Hi everyone, how are you doing? Can you please confirm if everything is good? Audio, video, everything is good? Okay. So I hope you people are doing great. So let's get started, right? So today we are going to solve many questions on shortest path, okay? And also we will do a complete analysis on Bellman-Ford. We will see that why this Bellman-Ford works, and also we will see the similarity between prims and digextra, which many students doesn't know actually. So let's just cover all of this today. So let's just get started. But before that, just let me know if everything is fine, which means audio, video, and everything is fine. Okay. So if everything is fine, then we can just start. Great. So let's get started. This is going to be very interesting session. Let's just get started. So let's just get started with the Bellman-Ford proof. Okay. I mean, many people might be knowing that why Bellman-Ford work. Many people might be knowing that what is this Bellman-Ford. So today we will see the proof of this. Okay. What is this proof? Like how does it work and why it is work? But before that, obviously, like I will first tell you that what is a Bellman-Ford, right? I mean, what is this algorithm? I will first go through the algorithm, and then we will also see the proof of this algorithm, right? So let's just assume that this is the graph that is given to you. Okay, let's just assume that this is the graph which is given to you, and these are the weights that are given to you. Okay, which means that A is a, let's suppose, source vertex, and from here I want to find out the shortest path to everyone else. So for example, a shortest path to C is this, right? From A to C, this is the shortest path, right? This is the shortest path from A to C. From A to B, this is the shortest path. It seems that from A to B, this is the shortest path, which means that this is 3 plus 6, which is 9. This is the shortest path from A to B. Okay, from A to C, this is the shortest path. From A to B, this is the shortest path. It seems like that, right? From A to D, it seems like that this is the shortest path. And similarly, we can find out other shortest path. For example, from A to E, from A to E, this seems to be the shortest path, right? Okay. So basically, like we need to find out the shortest path between A to every other vertex. Okay, to every other vertex. This is the problem, which is called single source, shortest path problem. Shortest path problem, right? Now, to solve this, we have two popular algorithms. Can you tell me those? One of them is Dijkstra, another one is Bellman-Ford, right? Bellman-Ford. So let's just see today what is this Bellman-Ford. How to solve the single source shortest path problem using Bellman-Ford. But before that, can you just answer me this question? Okay, just look at this question and then just try to see if you can answer me this question. So what this question is saying, it is saying that this is just a true false question. Let's suppose there's a graph which is given to you. Okay, let's suppose this is a graph which is given to you. Now in this question, they have just asked a very simple thing. Okay, just look at this question and try to see if you can answer this question. So what they're saying is that given this graph, okay, whatever is given to you, let's suppose that this graph is given to you. Now they are saying that given this graph, can you tell me that if we relax the edges in this marked order, which means what does this relaxation mean? See, if you relax this particular edge, it means that you are, let's suppose it is initially 0. Relax means considering, right? You are considering this edge. I have told all of this in the previous session. Okay, there is one more session. I will put link of that session in the description. Okay, there is one more session. We have already seen all of this in that session, right? Okay, so I mean the relaxation. What is this relaxation? We have seen what is this relaxation. Relaxation means considering, which means that if you relax this edge, then the distance between edge to b1, you will say current distance is 2. And then let's suppose you relax this edge, then you will say it is 4. Then you relax this edge, let's suppose this is 5, and then you relax this edge, which is 7. So basically the question says that consider the given graph and mark edges from the shortest path from edge to t. So they're saying, the question is saying that marked edges, which means this edge, this edge, this edge, and this edge, this is forming the shortest path from edge to t. I mean, it is given that this is the shortest path. Now what else they say? They say that if we relax the edges in the order of this, which means first edge to b1, then this, then this, then this. If we relax the edges also in this order, then we get the cost of shortest path, right? Yeah, even if you have not seen the previous session, doesn't matter. You can directly watch this session. Okay, don't worry about it. So this session is going to be very nice session. You just understand the proof of this Bellman-Ford. Before that, let's just see what is this question. This question is saying that suppose it is given that we already know the shortest path. See, there are two problems. One is that find out the shortest path from S to T. Okay, then you will explore. You will do whatever you want to do. The second problem is that second is saying that you already know the shortest path. For example, you already know the shortest path. Now they are saying if you relax this edge and then this edge and then this edge and then this edge, then at least you will get the cost of the shortest path. What do you think? So if you relax this edge, then this is 2, then this is 4, then this is 5, this is 7, right? So if you relax in this order, aren't you getting the cost of the shortest path? Tell me, is this true or false? This is true or false? Just tell me. See, see, for example, this is given to me, right? For example, if I don't relax in this order, for example, if I relax in some other order, for example, this is 0 and initially everything else is infinity. Okay, initially everything else is infinity, right? Everything else is infinity initially. Now you just tell me if everything else is infinity, this is infinity, this is infinity, everything else is infinity, then let's suppose you relax this edge, then you will be getting 2 here, right? You will be getting 2 here. Okay, and then let's suppose you relax this edge. So since this is infinity, then infinity plus 1, then it is again infinity. So basically it is again infinity. So you are relaxing this edge first, and then let's suppose you are relaxing this edge. You are not relaxing in the order which is given, which means suppose you are not relaxing in this order. First you are relaxing, let's suppose this, and then let's suppose this and then this. Okay, for example, suppose you are relaxing, first you are relaxing S to B1, and let's suppose afterwards you are relaxing B3 to B4, and then you're relaxing B1 to B3, and then you're relaxing B4 to B2. Let's suppose B4 to T. Let's suppose you're relaxing in this order, okay? Which means S to B1, then this will be 2, then B3 to B4, then this will remain infinity or infinity plus 1, doesn't matter. I mean, it is infinity only, right? And then B1 to B3, which means now you're relaxing this. Now you're relaxing this means you will make this what? You will make this 4. And now you're relaxing B4 to B2, sorry, B4 to T. Now it is again infinity, right? If you're doing so, are you finally getting the shortest cost, at least shortest path cost? No, right? If you are doing in this order, then it is not necessary. But the question is not this. The question is this, that if you are doing exactly in the same order of the shortest path, okay, this is exactly same order of the shortest path, then at least you get the shortest path cost. Then answer is yes, this is true, right? This is true. I hope you understood that what I'm trying to say. Now let's just label this question up, right? Now let's suppose they say that we are relaxing in the same order. Okay, I mean we are relaxing in this order only, in the shortest, this is called shortest path order, right? I mean you're relaxing in the same order, but let's suppose the question is twisted now. It is saying an intermix with some more relaxation, then also we get the cost of shortest path, which means they are saying what they are saying is that you relax in the same order, which means you relax S to B1, and then B1 to B3, and then B3 to, let's suppose, B4, and then B4 to T, right? You relax in this order, but in between, maybe here, maybe here, maybe here, maybe here, maybe here, in between what you're doing, they are saying that you're relaxing some other edges also, which means maybe here you're relaxing B1 to B2, maybe here you're relaxing, let's suppose, S to B2, maybe here you're relaxing this B3 to T. Okay, I mean in between you are mixing this up. So you're, as long as this order is concerned, you are relaxing in the same order. After this, you're relaxing in the same order, but you are intermixing with some other relaxations. Okay, you're intermixing with some. This is the question says, if we relax the edges in the same order that was earlier and intermix with some other relaxation, then also we get the cost of shortest path. Then what do you think? This is true or false? See, if you relax this, maybe I mean you can relax basically anything before that also. Maybe you relax this, right? You relax this. For example, what I'm trying to say, let's suppose you relax in this order only, but let's suppose you intermix also. Okay, you intermix some more relaxations. Okay, whatever relaxation you can think of, you can intermix that, right? Which means, let's suppose you are first doing it, which means it will be 4. Okay, I mean, initially everything is infinity. Initially everything is infinity. Okay, except this source. Now, if you do this, this will be 4. If you relax this, then let's suppose you're relaxing this afterwards. Okay, maybe. I mean, what I'm saying that you can relax in any order, but this order is fixed. I mean, as long as the relative order is fixed, relative order is concerned, then this order is fixed. Okay. So for example, you are relaxing now this. Maybe you can relax this will be 7, right? Now suppose at some point in time you're relaxing this. It will be 2, right? It will be 2. And now let's suppose you relax this. Tell me what is the earlier one? Earlier one is 7. Then 2 plus 2, what it will be? It will be 4, right? It will be 4. Now you tell me this is 4, right? This is 4. So this is 2, this is 2. 2 plus 2, 4. See, earlier it was 7. Now will it get updated or it will not get updated, right? It will get updated, right? It will be 4 only. So earlier it was 7, but now it is 4. So what does this mean to say? It means since it is shortest, see, the 4 is shortest, right? Since the 4 is shortest, so whatever was the earlier one, maybe 7, maybe infinity, or whatever was the earlier one, since I am the least one, since I am the least one, then it will always, this 4 will always overwrite whether it is infinity, whether it is 7, whether it is 12, whether it is 16, whether it is 50, whether whatever this is, right? Since 4 is shortest, that's why 4 will always overwrite this, right? This old number, because it has to be greater, right? Are you understanding my point? So even though you have intermixed, which means even though you have relaxed this and maybe relaxed this, or before relaxing these two, right? Even though you're intermixing, okay, it doesn't matter. Actually, after this 4, maybe let's suppose you are doing this, okay, maybe 4 plus 4, let's suppose this is 8. But the moment you do this is 4 plus 1. Want to update this 8 to 5? Tell me. You will update this 8 to 5, right? So what I'm saying here is that you first do this. Let's suppose, okay, for example, you did this S to B2, and then you did B2 to B3, and then let's suppose you did S to B1, and then B1 to B3, and then let's suppose afterwards you did you did B3 to B4, or maybe you did this B4 to B1 to B4. Okay, let's suppose after that you do B1 to B4. So this is B1 to B4, and then you are doing B3 to B4. Okay, then you are doing B3 to B4, and after that you can do anything else. Maybe this B3 to T or whatever, right? This B3 to T, and then let's suppose you are doing B3 to T, and then you're relaxing this B4 to T. Okay, then you're, let's suppose, relaxing this B4 to T. So what I'm saying here is that as long as this relative order is fixed, okay, this relative order is fixed, in between whatever you do, see here, I did B1 to B4. It was from infinity. It got updated to this is 2 plus 4. Let's suppose it got updated to 6. Okay, it got updated to 6 because this is 2 plus 4. Now, whenever I do this B3 to B4, right? Whenever I do this, then since this is shortest, it will always update to 5, isn't it? So what I'm trying to say here is that see, this particular path which I've written, okay, this is the shortest path in the light white color. This particular path is basically the shortest path order, right? The shortest path order. So whatever you do in between the shortest path order, you will always get the final shortest path, isn't it? Is this clear to everyone or not? That this question is clear? That consider the given graph. If we relax in this order and also intermix with some more relaxation, then also we get the cost of shortest path. So this is also true. If you understood this, then the proof of Bellman-Ford is just a byproduct of this question. Okay, then we will prove in just a minute. Okay, proof of Bellman-Ford will be just a byproduct of this question. Okay, if you have already if you have understood this, let me know if you have understood this particular question or not. Okay, so I hope you understood, right? Now let's just see that how Bellman-Ford work and how we can prove it, right? Now let's just see that what is this Bellman-Ford and how we can prove this. So before going to the Bellman-Ford, I need to make sure that this particular question, which is an easy question only, but it should be clear to everyone, right? What this question is asking and why this question is true. Let me know if there is anyone who have not understood this question, that why this is true. See, that is the shortest. See, ultimately you will update with the shortest. So this particular relaxation, right? This particular sequence will carry on the shortest thing. So even though in between you do anything, it doesn't matter, because ultimately, whenever you do this B3 to B4, it will update this B4, right? This will update this B4 to whatever is required. Okay, understood? Okay. Now let's just see how this Bellman-Ford work and why this work we will see. But let's just see the working of Bellman-Ford. What does this Bellman-Ford says, right? Okay, so let's just see how does this Bellman-Ford work. So it says, see that you have this particular graph. Then what you do? How many vertices are there? 1, 2, 3, 4, 5, 6. Right? These are the 6 vertices. So you run a loop for n minus 1 times. It says this. What is n here? N is a number of vertices, right? N is a number of vertices. Right? You run a loop for n minus 1 times. This is what Bellman-Ford says. And what will happen if you do so? Let's just see. Okay, how does this work? What will happen? Let's just see. See here. Now, given this particular graph, what you will do? You will say that, okay, I will relax in any order, whatever order I like, okay, because I don't know that what is the shortest path order. See, fortunately, suppose if I by chance know that this is the shortest path order, then if I want to find out shortest path from S to T, then obviously I will relax in this order only, right? But suppose I don't know what is the shortest path order, then I can relax in any order. Suppose I relax in this order, B2 to B3, okay, and then maybe after that you can relax S to B1. This done, okay, S to B1, and then after that, let's suppose you relax S to B2. Let me just write a random order here first, okay, then maybe, okay, so see, B2 to B3, this done, S to B1, this done, S to B2, this done, then let's suppose B4 to T, okay, this done, then let's suppose B1 to B3, okay, and then B1 to B2, and then let's suppose B3 to B4, right? And then suppose B1 to B4, and then B3 to T. So what I'm saying, that suppose I don't know in what order I need to relax. So for that I'm saying, let's just assume any order in which we want to relax. Okay, you can relax in any order, but it says that you have to relax how many times? You can relax in this order, this given order. Okay, let's suppose you can relax in this order, but you have to relax 5 times. Okay, 5 times you have to relax, right? So you can relax in any order, which means you can first relax this B2 to B3, which means you can relax this. So initially everything is infinity, so it won't matter. Now S to B1, now you relax this, so this will be 2, right? This will be 2, and then you relax S to B2, this will be 4, and so on, right? And then you relax B4 to T, which means this B4 to T, then this is infinity, this was infinity, so it is again infinity only. So anyway, like if you relax one time, then some values we will be getting, right? And then you keep on relaxing. You do this how many times? You can relax in any order, whatever you like to. You need to do it n minus 1 times, okay, which is 5 times. That's what the Bellman-Ford algorithm says. So maybe I can take a little smaller graph, and then I can show you that how the Bellman-Ford is working, right? Let's just take this graph, okay, and then let's just quickly see that how does the Bellman-Ford work. So let's pick any order. Maybe I can pick some order. Okay, here let's pick any order. Maybe I can pick some order, which is, let's suppose CB. Okay, so how many vertices are there? 4 vertices are there. So I need to relax 3 times, right? So let's just pick CB, and then maybe AB, Okay, CB, AB, and then maybe DC, and then let's suppose BD, and then let's suppose AC. Okay, let's suppose if we relax in this order, how many times we need to relax? Can anyone tell me? We need to relax how many times? Since these are the four vertices, we need to relax 3 times. Right? Now let's just try relaxing. CB, right? This CB. Can you relax? See, initially, let's suppose this is source. Initially, everything is infinity, right? So if you relax this CB, what you will be getting? Infinity minus 1. You will be again getting infinity. Okay, that's done. Now, AB, which means this, you will be getting this as 1, right? You will be getting this as 1. And then DC this, you will be again getting infinity. Then BD. So this will be 6 now. This will be 6. And then AC, this will be 10, right? So after one iteration, what is the distances? 1, 6, 10, and 0, right? After one iteration, these are the distances. But is this shortest? Is this shortest? Tell me, is this 10 shortest? Is this 10 shortest? May not be, right? 1 plus 5, 6, 7, 8. Maybe 8 is shortest, right? Okay, so these are not shortest actually. Fortunately, I think I have got, I think this is shortest, but it need not to be actually. Okay, after one iteration, and there need not to be the shortest path. Okay, so is this understood? That after one iteration, whatever I am getting, it is not the shortest. Okay, it need not to be actually shortest. Now let's just run it again. So I need to run 3 times. Okay, one is done, right? So I need to basically run it 3 times. 1, 2, 3. Now one time we have done. Let's just relax in the same order. Or maybe interestingly, see, in this second iteration, you can choose any other order also. Okay, you can, okay, for the second iteration, let's suppose for the second iteration, suppose I choose this order. Okay, for the second iteration, let's suppose I'm choosing this order where I'm basically relaxing this AB later on, and I mean at the last. Okay, so you can choose any order at any iteration. That's also very interesting part of this Bellman-Ford, which many student doesn't know. Okay, they think that okay, once the order is fixed, then we need to relax in the same order. No, it's not the case. You can relax in this order in the second iteration. So first relax CB. You will be getting 9, but it is already 1. So I think that will not get updated. Now relax DC. So relax this DC. This is 8, right? So it will get updated to 8. Now relax BD. BD is which one? BD is this one. It is already 6. Then AC. AC is this is 10 and this is 8. So it will not get updated, right? And then AB. AB is this. It is already 1. So second iteration is also done. After second iteration, we have got these as the shortest path. Now let's just run one more iteration, which is the third iteration. Okay, if you run third iteration, maybe you can run in any other order. Okay, maybe you can say that okay, now this time I will do AB here. Okay, and maybe you can say that okay, BD at the last. Okay, so suppose for the third iteration I am choosing a different order, AC BD. Right, now let's just relax this AB, so it will not change anything, right? And CB will also, I think, not change anything because it is already shortest. And then DC, it will also not change anything because it is 8. And then AC is this, and this will also not change anything. And BD is this, which will also not change anything. Anyway, we have run 3 times, and finally we have got these. Are these shortest? These will be definitely shortest. Okay, so I hope you little bit got that how Bellman-Ford is working. Okay, how it is working, how it works. What you need to do, you need to run it n-1 times, and that's all. So basically it says that if you run it 1 time, okay, then you will be getting the shortest path from source to the direct vertices. Okay, if you run it 1 time. So I will tell you what does this mean. But before that, you understand that if you run it n-1 time, then you will be getting the final distances, right? Okay. Now let's just see the more interesting part, which is that why does this work? Okay, why this Bellman-Ford work? Let's just see the more interesting part, which is that why this Bellman-Ford work, the way it works. Okay, now to basically illustrate this idea, let me just first of all tell you that the proof that we are going to see, okay, the proof that we are going to see is super easy. Okay, the proof that we are going to see is super easy, and also not known, not known to almost every aspirant. Okay, let's just see that what is this proof. And also the one more thing that I would like to say before I begin this proof, that the way we are going to prove is you will not find it anywhere else. Okay, I mean, even not in, I mean, basically, like, I don't know, maybe this proof is there, but I have not found the way we are going to prove now. Okay, I have not found that way. The most common proof that is available on the internet is basically using induction. Okay, but we are not going to use induction. Induction doesn't give you any intuition. Anyway, so now let's just see the proof of this. Okay, that why this Bellman-Ford work. This is super easy proof and not known to almost every aspirant. So let's just see that why this Bellman-Ford work. Bellman-Ford says that if you run it n minus 1 times, then you will get the shortest path distances, right? This is what Bellman-Ford says. But why? Why this happens? Let's just see. See, suppose that this particular path is the shortest path. Okay, which means that S to B1 this is shortest, B1 to B2. I mean, this is the shortest path. See, I'm assuming here that suppose somehow I know the shortest path. My claim is that our Bellman-Ford algorithm will discover this in not more than k steps. If this is basically, if this is like, I mean, this is k plus 1, right? So these are the k plus 1 vertices, and then we need to run it. So it is n, we need to run it n minus 1 times, which is k times. So if you run the Bellman-Ford algorithms k times, which means basically these are the k edges that we have. So this is first edge, second edge. Similarly, there are k edges we have. So if you run the Bellman-Ford algorithms k times, then it will discover this path. Okay, this is our claim. See, this is the shortest path, which means there could be other edges also. Maybe S to B1 is their edge. Okay, maybe B1 to BK minus 1. Maybe like this there is edge, like that there is edge, like this there is edge. There could be many other edges in the graph. Okay, I'm not drawing all the edges. What I'm drawing here currently is the shortest path. How I know it? Let's not worry about it. Suppose that this is the shortest path, and my claim is that my algorithm will discover this. How it is going to discover that? Let's just see. So I'm going to run it k times. So one time I will run it, right? One time I will run it. Second time I will run it. And similarly, we will run it how many times? We will run it k times, right? Okay. Similarly, k times. Okay. Now let's just see that how running this k times will always guarantee that you will get the shortest path here. Okay. So suppose this is the shortest path which is given to me. Now tell me that you relax in whatever order you want. Okay. Maybe you will be relaxing B2 to B3. See, tell me, if you relax in this order, let's suppose if you relax strictly in this order, won't you be getting shortest path in just one iteration? Won't you be getting shortest path in just one iteration? If you relax in this strictly in this order only, I think yes, right? To VK, I mean to all of this, you will be getting the shortest path in just one iteration. If you strictly relax in this order. But suppose I don't know what is the shortest path, so I can relax in any order. Maybe I'm relaxing this B2 to B3 first, and then I'm relaxing, let's suppose S to B1, and then I'm relaxing, let's suppose B1 to B2, and so on, right? And then I'm relaxing, let's suppose B4 to B6, B4 to B5, and so on. So basically, suppose I'm relaxing in this order. Okay. See, I don't know what is the shortest path, right? So I cannot relax in the shortest path order, but at least I can relax in some other order, right? Now, what will I do? I will relax. Okay, I will relax in some order here also in the second iteration. Maybe here. Okay, you can choose the same order. Okay, you can choose the same order. Doesn't matter. But you can also choose the different order. Maybe you will say, okay, B4 to B5 here. Maybe okay. So yeah, you can choose, as I told you, you can choose any order anytime, right? Maybe here B3 to B4. and B1 to B2, maybe S to B1, and then B2 to B3 or whatever, right? So you can again choose some other order here, here some order, here some order, here some order, here some order, and so on, here some order, and so on. Now let's just see that how Bellman-Ford works so beautifully. It says, interestingly, it says, see, if this is the shortest path, then do you remember the question that we have solved one like earlier? Do you remember this intermixed question? Do you remember this question? It says that if you relax in this order, even though you intermix something, okay, even though you intermix something in between, still you will be getting finally the shortest path, right? So for example, that this is given to you, right? So here in this particular question, we have seen that 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 for this, if you relax in this order, see, if you relax in S to B1, and then B1 to B2, and then B2 to B3, and then B3 to B4, sorry, S to B1, B1 to B3, S to B1, B1 to B3, and then B3 to B4, and then B4 to T, right? If you relax in this order, then ultimately you will be getting the shortest path. In between, maybe you can relax, you can intermix something, right? In between, maybe you can intermix something. Now suppose I say that you run it multiple times, right? You run it multiple times. First iteration, this is the second iteration, this is the third iteration, and so on, right? This is the fourth iteration, and so on. Here you are having any order, okay? Maybe this B2 to B3, right? I mean, any order you are having. This is the first iteration. This is the second iteration. This is the third iteration, and so on, right? Now here you are having any order. Maybe you are having, let's suppose, B1 B3, and then B4 T, and so on, right? Here whatever order you will be having, okay, here some order you will be having, here some order you will be having, here some order you will be having. Now ultimately, interestingly, don't you have, since you're relaxing all the edges, don't you have S to B1 from here? S B1 can't you have here? You will be having SB1 here. You have all the edges here. You have all the edges here, right? So what you will do? You will say, see, you will say that I will pick SB1. Basically SB1 is, let's suppose, this. Okay, SB1. I will say, okay, this is SB1. This is, let's suppose, B1 B3. I will say, okay, this is B1 B3. This is, let's suppose, B3 B4. This is B3 B4. This is, let's suppose, B4 T. Okay, this is B4 T. So here all other edges will be there. Here all other edges will be there. Here all other edges will be there, right? But it's not a worry to us. So what we are saying that you do in the first iteration you do any order, in the second iteration you do any order, in the third iteration you do any order, in the fourth iteration you do any order. But ultimately, you can pick this SB1 from here, B1 B3 from here, B3 B4 from here, B4 T from here, and you will say, see, I have relaxed in the shortest path order, right? Like there is an intermix, that is fine. There is an intermix of something, that is fine. But ultimately, haven't you relaxed in the shortest path order? See, if you finally relax in the shortest path order, right, you will be getting the shortest path cost. So what we are doing multiple iterations to make sure that ultimately we are relaxing in the shortest path order. So that is how you can prove it. Don't worry, let me just go over it one more time. So what I'm saying, let's suppose this is the graph, right? Okay. Now suppose this is the shortest path, which is this. Okay. Let's suppose this is the shortest path. Let's suppose this is E1, this is E2, this is E3, this is E4, this is E5, this is E6, this is E7, this is E8, this is E9. Okay. Let's suppose the shortest path is E1, E4, E6 and C7. Okay. E1, E4, E6 and E7, which means if you relax in this order, then you will directly get the shortest path from A to 6. Okay. From A to 6 if you want, if you directly relax in this order, then you will be getting. But let's suppose I don't know the shortest path from A to 6. So I might be relaxing in any order. Let's suppose in the first iteration, I'm relaxing, okay? In the first iteration, I'm relaxing in this order: E1, E2, E3, E4, E5, E6, E7, E8, E9. Okay. Let's suppose I do it multiple times, right? I am doing it multiple times. Okay, you can relax in the iteration wise also, you can change the order, but let's just keep the same order. Okay, let's suppose I'm doing it multiple times. Okay, now this is the first time I'm doing it, this is the second time I'm doing it, and so on, right? I'm doing it multiple times. Now what I'm saying here is that you want ultimately this order, right? Can't you pick even from here? Can't you pick e4 from here? Can't you pick e6 from here? Can't you pick e7 from here? And ultimately you say that, see, I have relaxed in even e4, okay, e6 and e7 order. Ultimately, aren't you relaxing in this order? Tell me. See, if you do it multiple times, then for any order you are making sure that you are relaxing in the shortest path order. Okay, let me know if you have understood this. So you can relax in any order, but if you're doing it multiple times, then ultimately you're making sure that this sequence is coming up, or any other sequence of shortest path is coming up, isn't it? So basically for 1 to 6, I'm saying that you can relax in any order, right? But if you're doing it multiple times, you are interestingly, you're making sure that this order is basically preserved. I mean, you will definitely get this order, or any order of your wish, whatever order of the shortest path was. Let's suppose it was e1 e5, let's suppose, okay, sorry, e1, let's suppose e1 e2, e1 e2 e3 e4 e6 e7 maybe, okay, e1 e2 e3 e3 e4 e6 e7, right? Let's suppose this is the shortest path order. Tell me, if you do it multiple times, if you do it multiple times, can't you pick even from here? Multiple time means that at least you do edges time. So how many edges are there? 9. Okay, sorry, these are how many vertices are there? 6. So you do 5 times. Okay, you do 5 times. So even e1, and then okay, from e1 you can't go to e2, so this should be e3. Okay, so suppose this is the shortest path order. So aren't you making sure that e1 e3, and from e3, okay, you have to have e6, sorry, I have written it e3, and then maybe e1 e3, and let's suppose e1 e3 e7. Okay, so let's not worry about it. Let's suppose this is the shortest path order, which is e1, okay, e1 e3 and then e7. So whatever order you follow here in the first iteration, in the second iteration, in the third iteration, in the next iteration, you can always say that, let me pick e1 from here, let me pick e3 from here, let me pick e7 from here, right? So this order, or whatever order of the shortest path, isn't it maintained? That is my question is. So this is definitely maintained, right? So all the shortest path orders are actually maintained, right? So what I'm trying to say here is that, see here, what I'm trying to say is this, that whatever, let's suppose this is the shortest path. Okay, let's suppose this is the shortest path. Now you will say, okay, let me pick this particular edge. See, I want to relax in this order, but in the first iteration, is it necessary that you will be relaxing in this order only? In the first iteration, is it necessary you will be relaxing? No. But combinedly all of the iteration, it is necessary that you will be relaxing in this order. If you combine all of these iterations, how? This, you pick S B1 from here, then B1 B2 from here, then this B2 B3, okay, wherever it is, then you pick B2 B3 from here, right? You pick B2 B3 from here. So combinedly all of this will make sure that, okay, S B1 and then B1 B2, then B2 B3 and so on, right? So in the one iteration, you can't make sure that, okay, that you are relaxing in the shortest path order, but you combine all of this iteration, then you will say, yes, you are relaxing in the shortest path order. No, it is not related to adjacency matrix power. Okay, so it is not related to that. So someone is asking, it is related to adjacency matrix power. No, it is not related to that. That is a different concept. So here, let me know, is this beautiful proof is okay to everyone or not? Okay. See, this proof, let me just tell you, it is not given anywhere. Okay, this proof is not given anywhere, and we have got many appreciation of this proof. You might be knowing Khushit, right? You might be knowing Khushit, who was AIR 11. of Go classes topper. I mean, he was a Go classes topper. So he particularly put a comment on the under this video in the Go classes channel, in the Go classes website. Okay, he particularly put a comment. I don't remember exact words, but awesome video and so on. And there are many other comments that we have got just for this proof. This is a very beautiful proof in the shortest path algorithms, right? So here we are saying that you relax in any order, but ultimately all of this iteration combinedly make sure that the shortest path order relaxation is there. Is this okay? Now there is a property which is called path relaxation property. Okay, there is a property which is called path relaxation property. It is also the same thing. It is saying let be the shortest path. Okay, suppose b0 to vk. Let's suppose this is the shortest path, right? If we relax in this order, v0 and in this order, even intermixed with other relaxations, then this is the distance and this is the shortest distance. Okay, this is basically a notation for the shortest distance. Okay, they are saying that the distance, this is a distance from v0 to vk, is actually finally the shortest distance. Let me know if this is understood to everyone or not. Okay, so this was the proof of this Bellman-Ford algorithm, that why this Bellman-Ford algorithm work, right? Why this Bellman-Ford algorithm work? So basically, what you need to do, you can say that okay, you can relax in any order, but ultimately all of these iterations, okay, combinedly all of these iterations are making sure that the shortest path order, okay, you can pick one edge from here, one edge from here, one edge from here. The shortest path order is actually maintained, right? Now the Bellman-Ford also says that if you let's suppose there's a negative edge, right? There's a negative edge, but let's suppose there is no negative cycle, which means this cycle is having, there's a cycle, but this is not a negative cycle, right? This is not a negative cycle which is having a weight of 4. So suppose there is a negative edge, but there is no negative cycle, then also Bellman-Ford work, right? It doesn't care whether there is a negative edge or not, but digester doesn't work. So here, let's suppose you're relaxing this. Okay, then what is the cost of relax here? Cost of relax. Do you need to maintain any heap or something? See, in digester we maintain all the vertex cost in a heap. But here we can just have the array, right? We can just have the array. Which means if you're relaxing that A to C, let's suppose this is A, B, C, D, E, and so on. It is 0 initially, and then everyone else is infinity, right? And now let's suppose you are updating some edge cost. Maybe let's suppose you are updating this 7. Then you can directly update this. Okay, you can directly update this. Basically, you do not need to maintain the heap. So here the relax cost is same as order of 1. I mean, it is same as update entry in array. Okay, in Digestra it was decrease key. In Digestra it was a decrease key operation, but here it is not decrease key. Here the relax is just update entry in array. Okay, so if we are running this, let me just tell you the time complexity here. If you are running this, for example, order of you are running this you are running this n minus 1 times or b minus 1 times, right? And then v minus 1 times you are relaxing the edges, right? Relax e edges. So to relax e edges you will take how much time? You will just take e time, because to relax one edge you will just take one time. So to relax e edges you will take just e time. So finally the time complexity is v into e only. Okay, order of v into e only. This is the time complexity of Bellman-Ford algorithm. Okay, I hope you understood that what is the time complexity. Here the relax operation is just update in unsorted array. Okay, update entry in unsorted array. which is just order of 1. So if you want to relax E edges, then in every loop you will be taking E time, right? So see here that what you need to do here, the relax is basically just a, okay, if you want to maintain the parent, you can do it, but here this D is just unsorted array. So relax is just update in unsorted array. In the Dijkstra, the same thing in Dijkstra was the decrease keys, because it was a heap. Okay. Okay. So I hope you understood that how this Bellman-Ford is working, and why this is working is more important. So in this particular session, I wanted to talk about the why part. Okay, I wanted to talk about this particular part, that why this Bellman-Ford work, because most of the aspirant doesn't understand that why this Bellman-Ford work. Okay. Now let's just see few questions here, right? So regarding the negative, wait, let me just tell you, negative edge, but no negative cycle. Okay, but no negative cycle. See, if there is a negative cycle, then no algorithm can work. Okay, it's not about the Dijkstra or something, or the Bellman-Ford, right? So if there is a negative cycle, then the shortest path doesn't even exist. See, if there is a negative cycle, let's suppose this is a negative cycle. This is 1, this is, let's suppose, 2, and then this is -5. Okay. Let's suppose this is S, this is source, this is your destination. I mean, you want to find out the shortest path from S to T, let's suppose. Okay. Then if there's a negative cycle, you can keep on revolving here, right? You can keep on revolving and you can keep on decreasing the cost. So here this is a negative cycle. Hence, shortest path doesn't even exist. Okay, shortest path from S to T doesn't exist. Okay, but if there is a negative edge only, okay, if there is a negative edge only, but there is no negative cycle, then Bellman-Ford can work very fine. Okay, then Bellman-Ford can work. So what does Bellman-Ford says? It says that, see, you run the algorithm. For example, there is any, let's suppose this is the graph, right? So it says that you run the algorithm n-1 time. Okay, and then let's suppose I'm running n-1 time. Then what it says is something like this. See, you run the algorithm here n is basically how much, how many vertices are there? 1 2 3 4 5. So it says that you run it 4 times, right? Now why we are running it 4 times? Because after 4 times from this A, if A is a source, then after 4 times we will be getting shortest path from A to everyone else using at most 4 edges. See, if there are 1 2 3 4 5, right, then any shortest path from A to any other vertices, for example from A to B, it just contains 1 edge, right? From A to C just contain 1 edge, for example. Then any shortest path from A to any other vertex cannot contain more than 4 edge, because if it is 5 edge, then it is basically a cycle, right? If let's suppose you have 5 vertices, 1 2 3 4 5, and from this, if you want to go to this, okay, then if you are taking 5 edges, let's suppose 1 2 3 and then maybe 4 and then 5, if you are taking 5 edges, aren't you getting a cycle in between? And shortest path obviously cannot contain the cycle, whether it is positive or whether it is negative, right? So I mean, if it is negative, shortest path do not even exist. If it is positive, then why will it contain? Isn't it? Won't you directly go? Why you will take this cycle? So if you are having, for example, if you are having 5 vertices, okay, these are the 5 vertices, then only at most 4 edges are needed. Okay, at most 4 edges are needed for the shortest path. are needed for the shortest path. Let me know if that is okay to everyone or not. At most 4 edges you will be needing, right? Okay. Okay. So let me know if there is any doubt till this point. So I hope you understood that how the Bellman-Ford is working. See, the like mostly in this particular session, I don't want to talk about the details of that. The example of the Bellman-Ford, but mostly I wanted to talk about that how and why this is working. Okay, why the Bellman-Ford is working the way it is working. Okay, so let me know if there is any doubt till this point. Cool. So now let's just move to the next things, right? Now let's just move to the next thing. So let's just talk about. Let's just talk more about this Bellman-Ford only. Okay. See, let me just bring you. Let me just bring you a screenshot here of many other people. Okay, who have earlier understood this Bellman-Ford proof. For example, this is a screenshot from our website. For example, see here that what this Khushit is saying. So Khushit, if you know, he has got AIR 11 in gate 23, right? 2023. So he has got AIR 11 in gate 2023. So he for this Bellman-Ford, he has already commented on this amazing explanation. There are many other students who has commented out for the proof of this Bellman-Ford. Okay, that how this particular algorithm is working. Okay. So now if you have 5 vertices, then there are at most 4 edges that you need. So if you're running it 4 times, then Bellman-Ford says that if you, let's suppose, run it 1 time, okay, if you relax the edges 1 time, then Bellman-Ford says that you will be getting the shortest path using at most 1 edge. Okay, at most 1 edge. If you're doing it 2 times, you are relaxing all the edges 2 times. Okay, if you're running the loop 2 times, okay, then you will be getting the shortest path using at most 2 edges. If you're running 3 times, you will be getting shortest path at most 3 times. If you're running it 3 times, then you will be getting the shortest path using at most 3 edges. If you're running it 4 times, then you will be getting shortest path using at most 4 edges, like this. Okay. So Nagendra is asking that for the dense graph, okay, which means E is same as V square. Dense means E is same as V square. Since the time complexity is V into E, and for the dense graph, we will be taking V cube, right? That is true. We will be taking V cube. Then he is saying that the algorithm take N cube and all pairs also take the same time. Then what is the advantage of this? Yes, for the dense graph, there is not much advantage. Yes, I agree. For the dense graph, there won't be much advantage. Okay. So if the graph is dense, then it will end up taking this V cube time, right? Because you need to relax many edges many times. Okay. Now let's just see for the negative edges what is the case. So if the graph is having negative edge but no negative cycle, then Bellman-Ford work fine. And let's suppose there is a negative cycle also. Okay, for example, let's suppose this is minus 60. If there is a negative cycle also, in that case, what will the Bellman-Ford will do? You run it 4 times, and then you run it one more time. Okay, this is called cycle deduction. Okay, this is called cycle deduction. You run it one more time, right? This is called cycle deduction, which means that in this one more time, if we are seeing that okay, there is some change in some distances, then there must be the negative cycle. So which means that Bellman-Ford can detect the negative cycle also. Bellman-Ford can detect detect negative cycles if it is reachable from the source. Okay, which means suppose there is a negative cycle which is reachable from the source. Okay, suppose the cycle is negative, then this is 1 2 3 4 5 5 vertices are there. If you relax all the edges 4 times, then there is supposed to be the final answer. But if you relax all the edges one more time, 4 plus 1, right? This is n minus 1, and then this is one more time. Okay, one more time. Then since there's a negative cycle, so that's why one of the edge, if you relax it, then at least one of the distance will get reduced. So in here, if there's a change in last iteration, if there's a change, then we will say there's a change, then we will say that negative cycle is present, right? Okay. Now, suppose there is a negative cycle which is not reachable. Okay, which is not reachable. Suppose this is the negative cycle which is not reachable from the source. Maybe you have the cycle here, right? Then whatever you do, it is always infinity, right? Whatever you, I mean, if you relax this, you relax this, you relax this, it is always infinity. So if the cycle is not reachable, then let's suppose that this is not even the cycle. Okay, let's suppose this is the case. So if some vertices are not reachable from the source, if some vertices are not reachable, then ultimately this will remain infinity. Now you don't know at the end of the iterations, you don't know whether this infinity is because of the cycle is there. I mean, this is the infinity. Then at max you can say that it is not reachable. But can you say that there is a cycle? No, there may be may not be the cycle, or maybe the cycle. So after Bellman-Ford, let's suppose some of the vertices remain to be infinity. Then what we can say? If some vertices are infinity after Bellman-Ford, shortest distance is infinity, then can you say there is a negative cycle? No, there is no negative cycle. There may be negative cycle also. Then what you will say? That unreachable vertices. Okay, unreachable vertices. Can you say anything about the cycle if the vertices are not reachable? No, we can't say anything about the cycle. We can't detect the unreachable cycles, right? So we can't detect the cycle here. Okay. Now let's just solve more questions and let's just try to understand this. So this is a question which is saying run this Bellman-Ford shortest path algorithm on this graph, specifically fill this table below. Can you run this? Okay, can you try running this and then just fill this? So if you run it n iterations, then there won't be any change in the last iteration. Okay, if you run if there is no negative cycle, then there won't be any change in the last iteration. So now let's just see that what are these values. So initially this is 0, everything else is infinity, right? Okay, everything else is infinity. Now suppose you relax this. Okay, you're relaxing the A, B, C, D, E. Number of edges. So maybe I think you are relaxing in this order. Let me see the order in which they are relaxing. Okay, I think the order is not given here. So you can relax. Let's not worry about this table. So you can run the Bellman-Ford algorithm here. So you can relax in any order, but how many times you need to relax? This is 2, 2, 4, and 5. So you need to relax 4 times, right? You need to relax 4 times, and then one more time. 4 times plus one more time. Why this one more time? To detect whether there is a negative cycle or not. So you can relax it, right? You can relax this. You will be getting -2 here, right? And then you can relax in any order, but you have to relax this 4 times. So once you relax this 4 times, 1 time, 2 times, 3 times, and 4 times, right? So this is the first iteration, second iteration, third iteration, fourth iteration. Then you will be getting the shortest path. Okay. So I think you can do this question as a homework, because this is just a relaxation. So maybe you can relax it. Let's suppose you can relax this -2, then you can relax this. This is -5, and then maybe you can relax this. This is -10, and then let's suppose you relax this. This will be 2, and you need to relax this 4 times actually, all the edges, right? Okay. Now similarly, I think you can do this particular question. Here also they are asking, can you run the Bellman-Ford algorithm? Okay. Now let's see this question which I have taken from Princeton University. So what they're saying, let E be the edge with the weight 7. So they are saying that there is an edge, okay, with the weight 7. Suppose that during the generic shortest path algorithm, distance to B is 16. Okay, I mean till now they are saying, let's suppose till now we have found out that distance to B, distance to B means till now maybe the distance to B is 16. So you can say that this is from S to B, the current distance is 16, and from S to W, the current distance is 25. Okay. Then what will the pair of distance to B and distance to W after relaxation E? So if you relax this, if this is 16 and this is 25, then if you relax this, then what it will be? What will be this distance? Can you tell me? This will be 23, right? So only this will change. So if you relax this, then distance to W will change only. So I think this will be 16, 23. So B is the correct answer here, isn't it? Let's just see, B is the correct answer. Now let's just see the next question. What is the order of the growth of Dijkstra algorithm running time if we don't store distances in the priority queue, just keep the array? Okay. So do you remember for the Dijkstra, what is the time complexity? Do you remember? Time complexity of Dijkstra? Tell me. So this time complexity is basically in Dijkstra what we do. Do you remember? Basically we keep on taking, right? We keep on taking one vertex at a time. So we extract v times we extract or delete min. Okay, we maintain a heap of vertices, right? Heap of vertices. So we delete min v times, and then each edge we relax at most one time. So relax edge, right? So here this relax cost is nothing but decrease key. Okay, here this, since it is a heap, so relax is nothing but decrease key. So you can say that if you maintain heap, then this is the time complexity. I mean delete min, which is extract, and then decrease key. But they are saying that you are not maintaining the heap, you are just maintaining the array. So in case of array, I think the decrease key will be order of 1, right? You can directly decrease. Let's suppose this is unsorted array, you can directly update. Okay, this is update in array. Okay, this is order of 1. But delete min, so if you want to delete, then maybe you need to find out the minimum, right? First of all, you need to find out the minimum. Then how much time it will be taking to find out the minimum? Order of n, which is order of v, right? So I think v square plus e. And e can at most be v square, so ultimately it is v square only, right? So how much? V square, because v square plus e, and e can at most be v square, so that's why it is v square only. Okay. Yeah. Now let's just see this question. What they're saying, consider a simple version of Bellman-Ford algorithm where we initialize distance to be to 0 and every other distance to infinity, then fix the order of the all edges. Okay, so they are saying we fix the order of all edges and relax them in this order v times. Okay, if there are no negative cycles, we know this procedure will result in the array distance to be containing the distances from S to B for each v. So they are saying we know this procedure will result in the array distance to be containing the distance from S to B for each v. So basically they are saying if there are no negative cycle, then this algorithm will work fine. Suppose we perform no actions in addition to above, and the graph does have the negative cycle accessible from S. Which of the following must be true? So now they are saying there is a negative cycle, and we are doing it v times, which means v minus 1 times and one more time. And there is a negative cycle, accessible or reachable from S. Okay, reachable or accessible from H. Then which of the following is true? At the end of the process, at least one of the distance values will be negative. Do you think? See, it will get decreased. See, from this b minus 1, if you do it one more time, then it will get decreased. The decrease will happen, right? Decrease will happen. But it is necessary it will finally be negative? Tell me. Need not to be, right? So at least one of them will decrease, but ultimately it will be negative? Need not to be. Distance to S must be negative, which means distance to source is 0 only, right? It need not to be negative, right? I mean, it is negative only when this distance to be, I mean, it is very much involved in the cycle, and ultimately, basically, we relax in the order such that ultimately it is negative. I mean, it may be negative, it must be negative. It is not the case. It may be negative, but must be negative, may not, need not to be. The execution as described above will crash. No, why will it crash? So none of the above, right? So none of the above is the answer here. If we continue the process indefinitely, one of this will eventually be negative. Yeah, eventually be negative, but this may take longer than V rounds. So in V minus 1 rounds plus 1 rounds, so here it will decrease. Then if you do it one more time, then again decrease. If you do it one more time, again decrease. But eventually it will be negative. But in just V rounds, need not to be. Okay. Okay. Now let's just see this question. What they are saying. On a connected directed graph with only positive weight edges, Bellman-Ford runs asymptotically as fast as Dijkstra. So Bellman-Ford runs in V into E times Dijkstra. Okay, Dijkstra runs in V plus E log V times, right? I mean, basically V into log V plus E into log V, right? This is delete min, this is decrease key. V times you delete min, E times you relax the edges. V rounds of the iteration is sufficient condition to find a cycle. Yes, V rounds is sufficient if the negative cycle is reachable from the S. Okay, if it is reachable from the S, then V rounds are definitely sufficient, right? Okay. So what they are saying is that director with only positive weights, Bellman-Ford runs asymptotically as fast as Dijkstra. So what do you think? No, right? Bellman-Ford is this B into E. It is B plus E log B. These are not same. So basically it is false, right? See here. Okay. So these are not same. Now let's just see this. So they are saying G is a directed graph with negative edge weight but no negative cycles. Which of the following hold for the Dijkstra algorithm? Dijkstra will always give the correct output since there is no negative cycle. Tell me. Dijkstra will always give the correct output, do you think? If there is a negative weight edge, we have seen this in the previous lecture. For example, this. See, let's suppose this is 1, this is 5, this is minus 10. In this case, from S to T, Dijkstra will give 1, right? Dijkstra will give 1, but ultimately it is minus 5. So there is no negative cycle. It doesn't have a cycle. But still Dijkstra is wrong here, right? Still Dijkstra is wrong. Okay. So, no, that is not the case. Dijkstra algo may not give the correct output. Yes. So, let's suppose this is MSQ question. So, yes. Dijkstra algorithm may fail if we add large positive weight to every edge, then okay, but see, Dijkstra may fail, but if we add large positive weight edge, we have seen this in the previous lecture that if we add positive weight edge or something, or add or subtract, then the Dijkstra, it doesn't guarantee that Dijkstra will work, right? Even the shortest path may also be changed. So that's why this is false. May not terminate. No, it always terminates. Okay, it has the fixed time complexity also. It doesn't have the infinity time complexity. Tell me, Dijkstra is having infinity time complexity? No, it is basically having the fixed time complexity, right? It doesn't depend on the input, okay, for the time complexity. So anyway, so basically, may not terminate. No, it's not the case. It always terminates. Extra always terminates. Right? So hence, B is the correct answer, right? Okay. Now, let's just see this question. This is little tough and tricky question. So what they're saying, given an undirected graph, okay, weighted with the positive integer weight edge weights. Now, what they're trying to say, let's just see. Okay, so let's just see what they're trying to say. Find the path sorted. Okay, we want to find the shortest path from U to B with the below condition. The conditions are as follows. If two paths from U to B are of the same cost, we will choose the path with the fewer edges. Okay. Okay. So basically we want to find from U to B, but we will choose with the fewer edges. If multiple shortest path from U to B, then with the same number of edges, you can choose any such path. Okay. Now let's just see this particular question. What they are saying. Let me go to the next page. So let G be the graph with E number of edges. We want to add some constant to each weight and modify G to G dash. Okay, so we want to add some constant and we want to modify the G to G dash such that by applying Dijkstra on G dash we get the shortest path in G as specified the given condition. So basically they are saying that even if we add, then also we are getting the same shortest path. I mean, that's what we wanted. Okay, that is, this is the shortest path in G dash from U to B, then the shortest path in G with the least edges. Okay, anyway, so basically they are saying that what we should be adding such that the shortest path actually doesn't change. Okay, so maybe let me just tell you that what they are trying to say. See, they are saying that there is a graph. Okay. Now in this graph, there is a negative edges. Okay, there might be the negative edges also. Now what they are saying, let's suppose it's -3 or something. Then we want to add some positive constant. Let's suppose +100 everywhere, such that ultimately the shortest path doesn't change. Okay, so see, it is given that graph is having integer edge weights. Okay, all the edge weights are integer. The graph is having all the edge weights as integer. So now suppose if we add, suppose all edge weights are integer here. Okay, this is the old graph, and now let's suppose earlier x was greater than y. Okay, I mean, maybe there is a path x plus y is greater than p plus q or something. Okay, p plus q. This was earlier. But if you add some edge weights, then it might be possible that, see here, that if you add some edge weights, maybe let's suppose this is 1, this was 4. Okay, so the shortest path is this, right? Currently the shortest path is this, but if you add some edge weight, then it might be possible that the shortest path may be changing. Let's suppose you add 5 everywhere, or maybe 6 or 10 everywhere. If you add 10 here, if you add 10 here, if you add 10 here, so what is the now shortest path? Okay, if you do +4, so in general the shortest path, +10, in general the shortest path may change after adding, right? So earlier this was the shortest path, but now this is 14, which is the shortest path, right? This is shortest now. So in general the question is saying, see, in general the shortest path may change, but the question is some different. They are saying that what we should add such that the shortest path doesn't change. For example, see, earlier this 1 plus 1, which was shorter than 4, right? Now in this, so basically earlier if I have compared, let's suppose this x plus y and p plus q, maybe this x plus y was greater. Okay, maybe this x plus y was greater. But if you, let's suppose, if you add some weights, then in this path you are adding two weight. In this path you are just adding one weight. We have seen that in the previous lecture only. So here you are adding, let's suppose, only one weight, but here you are adding two weights. So after that, maybe this is greater. That's what it is happening here, right? So it is uneven, right? Here you are adding 20. In this path you are adding 10. Now they are saying, if you have, let's suppose, if you have earlier this relationship, then in each path, let's suppose in each edge I add 1 upon e. Okay, I just add 1 upon e. So in any path, since there are e edges only, I will not be able to add more than how much? If I'm just adding in any edge, if I'm just adding only 1 upon e. Okay, this is what one of the options says, that if you're adding just 1 upon e. Okay, this is an interesting option. If you're adding just 1 upon e, then let's suppose here you are adding 1 upon e. In this also you are adding 1 upon e. In this also you are adding 1 upon e. Everywhere you are just adding 1 upon e, let's suppose. Then earlier, whatever it was, at most in any path you can add e, or maybe just strictly lesser than e, right? Because any path will be having at most e minus 1 edges, or maybe n minus 1 edges, basically, right? So basically what I'm trying to say, if there are two paths, okay, if there are two paths, then in one of them, see, there are e edges only, so at most you can add e in one of them, right? And since there are two paths, so maybe just lesser than e. Okay, something lesser than e, you will be, sorry, not e, 1. See, if you multiply by the e, then it will be 1 only. So if you are adding 1 upon e, 1 upon e, 1 upon e everywhere, in combinedly in all the edges, how much you are adding? Just 1. So in one path, see, in all the path combinedly, you are adding just 1. In all the edges combinedly, you are just adding 1. Total, you are just adding 1. So here you are adding, just suppose, 0.5, right? And here you are adding maybe let's suppose 0.2 or something. So if earlier this x plus y was greater than p plus q, if everything was integer, they are saying they are integer weights, then at least this must be greater at least 1, which means it will be at least 5. It will be, I mean, if it is 5, then it will be, it can be at most 4, right? Or maybe this is 3, in the sense that it cannot be 4.9, because everything is integer, right? Since everything is integer, it cannot be 4.9. So if it is 5, then, I mean, one sum of the edges of one path is 5, then sum of the edges of the another path is, let's suppose, 4. Then here, if you add something lesser than 1, 0.1, 0.5, 0.6, even if you add something lesser than 1, here even if you add something lesser than 1, since the difference is at least 1, can this inequality be reversed after adding? Can it happen like this? Tell me. Can this inequality be reversed after adding? So the answer is no, right? See, if 5 is greater than 4, or 5 is greater than any other integer, let's suppose 3 or whatever, right? Then at least one difference is there. Now, if you are adding lesser than 1, whatever you add, 0. Maybe least, okay, 0.001. If you are adding lesser than 1 here, and if you are even adding greater than, lesser than 1 here also, you are adding lesser than 1 here, then this inequality can't be reversed. Why? Because you need to add at least 1 here. At least 1 you need to add. Since you need to add at least 1 here, so you can't reverse this inequality. So earlier, whatever was the shortest path, see, here the shortest path got changed because we are adding plus 10. But let's suppose we are adding, everywhere we are adding 1 by 3 only. Okay. So here we are adding 1 by 3, here we are adding 1 by 3, here we are adding 1 by 3. Now can you tell me the shortest path again? The shortest path is still same, right? If you are adding 1 by 3 everywhere, then the shortest path is still same, because you are not adding enough, right? So whatever was the earlier shortest path, it will remain same even if you are adding 1 by 3. But if you are adding 10, then the shortest path may change. So basically, if earlier this is the relationship, okay, then whatever you add in this 3, you can't change this inequality if you are adding lesser than 1 here, right? So this is what question says, that we can add 1 by e at least, okay, each edge width in the shortest, which is the same edge, okay. we can add 1 by e. So 1 by e is fine here. This was one of the test series question and it was very tricky question. Okay, this was one of the test series question, so it was very tricky question that we can add 1 by e and the shortest path won't change. Now can you tell me if, let's suppose this is a source. Okay, I mean there are many other things, but let's suppose this is a source. See, the problem is happening because I am having unfair addition, right? I'm basically having for example, in this case I'm having 20 addition here and 10 addition only here. But let's suppose I add fairly. Okay, how can I add fairly? Suppose I say I add only in these two edges. Let's suppose I add only in this edge 10, in this edge also 10. Basically I add only in the edges which are outgoing to this particular S. Okay, which are outgoing to this particular S. Then will the shortest path change? See, if I'm adding only to the edges, not to the all edges, if I'm adding only to the edges which are outgoing to the S, then also shortest path won't change. Okay, in that case also shortest path won't change. If I'm adding only to this edge and only to this edge only, then also shortest path won't change, because any path will at least any path going here, right, going here will contain either this edge or this edge. So basically in every path we are just adding evenly. We are not adding 20 here or 10 here or something. If we are adding 10 here and then we are adding 10 here only. So suppose if I ask you this question, then what will you answer? Okay, let me just go to that question. Just a second. Yeah. So suppose if I ask you about this option D, if the weights of all edge leaving S are increased by 2023, then any shortest path from S to T in G in the shortest path is remaining same. See, if the weight of all edge leaving S only, if I am increasing all the weights leaving the source only, okay, leaving S, if I'm increasing all the weights leaving the source, which means I'm not increasing anything else, I'm increasing only these edges, then this option is true. Okay, if I'm increasing only these edges which is leaving S, then I'm actually evenly increasing in all the path. Okay, I'm evenly increasing on all the path. Then this is okay. Then this D is correct. But in general, if I ask you if all the edge weights of G is increased, if all the edge weights are G increased, and then okay, this is minimum span tree. But let's suppose the option is that then shortest path doesn't change. Then is this true? Then shortest path is same in the modified edge weighted graph. Is this true? Then it is false, right? Then it is false. But if I'm only adding to leaving S, then it is true. Okay. So I hope you understood that what do I mean to say here, right? Now, actually there are many other questions that we can discuss, but the crux, I hope you understood, right? The crux of this particular session is the proof of Bellman-Ford. Okay, the proof of Bellman-Ford, that how the Bellman-Ford is working and why it is working, the way it is working. Now let's just solve this question which has been asking GATE 2009. So what they are saying, which of the following is your correct Bellman-Ford shortest path algorithm about are correct about the Bellman-Ford shortest path algorithm? It always find a negative weighted cycle. Need not to be, right? If it is not reachable, can't find if it is not reachable, right? Can't find if it is not reachable from source. From source. Find whether any negative cycle reachable from source. Yes, that is true. So only Q is true here. Okay. So I hope you understood that here in case of Bellman-Ford, only Q is true. I mean, it can't find if it is not reachable. Okay. Now, suppose we want to find all the cycles. See, Bellman-Ford in general can't find non-reachable cycle, right? Non-reachable, it can't find. But suppose we want to find non-reachable also, then what will you, non-reachable cycle also, then what you will do? Then what modification we need to do? Can anyone tell me? So that's very simple actually. What we can do, we can have a new graph which is G dash, which will say that okay, whatever is the earlier graph, let's suppose this is the earlier graph, right? Okay. And there is a non-reachable cycle in this earlier graph. Non-reachable, maybe negative cycle. Now, what will I do? Okay, if I want to find out the non-reachable cycles also, right? So this is the old graph. Then I will add one vertex and will add edges to all the vertices from this to this. And you can keep all the edge weights at 0, okay, or maybe 1, whatever you want, you can keep that, right? Doesn't matter. So let's suppose these all edge weights are 0, and let's suppose this is a vertex Q. Now, is this negative cycle reachable from Q? See, it was, let's suppose, not reachable from this S, but at least this is reachable from Q, right? Since this is reachable from Q, since this negative cycle is reachable from Q, that is why, what do you want to say? No, we will have this source session only. We will have this source session only. I'm just about to finish this session. Okay. So see here that if I want to check this negative cycle, okay, if I want to check this negative cycle, if it is not reachable from S, then I will modify. Okay. If I want to check whether it is whether there is a negative cycle or not, then I can modify this graph as G dash. Okay. And then I will run Bellman-Ford now. Okay. So I will say that, okay, now from this source, using this as a source, from this source, the cycle is at least reachable. Now I can run Bellman-Ford, right? I can now run Bellman-Ford. So I hope you understood that even though if it is not reachable, then what modifications are needed? What modification do you need to do? Just have one more vertex, right? Just have one more vertex. So that is all you need to do here. So this is all about this session. I mean, I just wanted to give you the flavor that why Bellman-Ford is working the way it is working. Okay. So that's all for this session. Actually, I wanted to discuss this Prim's Dijkstra difference also. That's also very nice. But we will discuss this in the next session. Okay. In any other session, we will discuss. I don't want to make this session that long. I just want to keep it for the Bellman-Ford proof. This Prim's versus Dijkstra and other questions that are there. Okay, there are many other questions that I wanted to solve, but I don't want to make it too long. So we will solve all of these questions in the next session or in any other session which will be there if we have for algorithms. Okay. So let's just keep this session here only. If you truly understood, right? If you truly understood the Bellman-Ford proof, that how this Bellman-Ford is working. So it is actually, let me just remind you, it is actually very, very intuitive proof, which says see here, see, which says that you can basically pick, right? You can pick the shortest path order in the multiple iterations. You can pick from the multiple iterations you can pick. So if you really understood, then just let us know in the comments. Okay, in the comments, just let us know. Let me just tell you this proof. This proof is not available anywhere. Okay, this proof is something that I have understood over the time. So after reading, you can say that after reading couple of resources and after spending enough time in this particular proof, I have got to know, okay, that's how we can prove it. Otherwise, there is an induction proof which is non-intuitive. Induction proof is available everywhere. You can just search Bellman-Ford proof, you will find the induction proof, which is not an intuitive proof. Okay, cool. If you really understood this proof, then please let us know in the comments. Okay, so thank you everyone. Take care. Bye bye.